Hey everyone, welcome back to physics. This is going to be lecture 27 of the course. And in this section, we're going to work on a few additional problems and examples of work and kinetic energy. So let's go ahead and jump into that. And we'll call this section 5.4, Problems and Examples. Specifically of work and kinetic energy. So I've got 4 problems picked out that I think will help to kind of underscore some of the relationships, some of the concepts that we elaborate over the previous couple sections. So the first one goes like this. The first one, a block of mass 5 kilograms is initially at rest. A block of 5 kilograms is initially at rest on the top of a frictionless incline that makes an angle of 30 degrees with the horizontal. Okay. The block slides down a distance of 8 meters before reaching the bottom. The block slides down a distance of 8 meters before reaching the bottom. Okay. And so then we got a couple things we want to know about this, but let's think. So it's a simple enough setup. We've got an incline here, 30 degrees, and we've got a block up at the top, 5 kilograms, and it's just going to slide down this thing frictionless, right? And so the distance it's going to slide is 8 meters. Okay, that'll be from the top to the bottom, 8 meters. Okay, now so the questions are, first, find the work done by gravity as the block slides down the incline. Find the work done by gravity, okay, as the block slides through this 8 meters. The second question is find the kinetic energy of the block at the bottom. Find the kinetic energy of the block at the bottom. Okay. And then the third thing is let's find the speed at the bottom. Okay, so these are kind of basic. Find the speed of the block at the bottom. These are kind of basic applications of work and kinetic energy and the work energy theorem. All right, so let's first, we've got the picture here. Let's think about what the free body diagram looks like. All right, so you've got the weight of the thing pulling it down in this direction like this. You've got a normal force that's perpendicular to the incline, right? And then really the force that's going to drag this thing down the incline is the force of gravity. But of course we have to think about gravity as having an x and a y component. And so really the part that we're interested in looks like this, isn't it? All right, so this is what I'll call F. And you can see that that's going to be, you got your 30 degree angle here, your 60 degree angle there. So it's important to note that the angle between the force doing the work, gravity, and the displacement is not 30 degrees, it's actually 60 degrees, isn't it? It's this angle here that we're interested in. Okay. But once you recognize that, then the work done by gravity is just equal to the force times the displacement times cosine of theta, where theta is the angle between the two, right? This is the scalar product. And so what do we get? We get 5 kilograms times 9.8 meters per second squared, right? That's the weight, the force. And really that would be times cos 60, which I'll put in here. I'll just put cos 60 degrees. And then S is the displacement, which is this 8 meters that the block is dragged through, right? So you multiply all this together, you get 196 joules. Right, so the work done by gravity in dragging this block down this incline is 196 joules. Okay, so this is the work done by gravity. That's the first part. Now the second part asks, what's the kinetic energy of the block at the bottom? Well, this is going to be an explicit use of, a very straightforward use of the work energy theorem. So the work energy theorem says that the total work is equal to the change in the kinetic energy. Now, at the top of the incline, K1, the energy is 0, right? Because the velocity is 0. It starts at rest. So this is 0. Right? So that means the total work is equal to the ending kinetic energy. Well, the total work in this case is just the work done by gravity. There's no frictional force to be concerned about. There's just gravity making this thing slide down, right? So K2 is just equal to the total work, which we just found. Right? So that one couldn't be easier. You just got to recognize that the initial kinetic energy is 0, the final kinetic energy is the total work. Okay. All right. And then the speed, this one also is very straightforward. You just have to know what kinetic energy is, how to calculate it, what quantities it consists of. So K2 is equal to 196 joules, and we know that K2 is equal to 1/2 times the mass times the final velocity squared. So that's 1/2. The mass is 5 kilograms. The final velocity is unknown. That's what we need to solve for. Okay, so it turns out V2 is going to be equal to the square root of 196 joules times 2. We're going to basically invert and we're going to multiply it by, well, divide by 5/2, right? So that means we have to multiply by 2 and divide by 5 kilograms. And that is going to give us the velocity. The velocity turns out to be about 8.86 meters per second. Right, so just letting go of this block on this frictionless surface is going to start moving pretty fast, actually. And by the time it traverses 8 meters, it's going to be moving at almost 9 meters per second. Okay. All right. Perfect. So that was kind of a straightforward problem. The quantities given just kind of mean, you're just going to have to calculate the force of gravity, calculate the work. About the only tricky part here is to make sure that you are thinking about the angles correctly. You just want to make sure you're not, using the wrong angle. If you use 30 degrees, you're going to get quite a different answer. All right, very good. What's next? Another problem. And all of these problems they're all quite different, but they all start with just a block of mass something. So example 2 starts by saying a block of mass 3 kilograms. A block of mass 3 kilograms moves along a frictionless horizontal surface. Maybe I should have put friction into some of these problems, but that's okay. So a block of mass 3 kilograms is moving along a frictionless horizontal surface. It starts with an initial speed of 2 meters per second. An initial speed of 2 meters per second. Okay, and we'll say at position x equals 0 meters. We'll just kind of coordinatize things a little bit. Now, as it moves, it's acted upon by a variable force. As it moves, it is acted upon by a variable force. Right, so that means our work equation is going to be a little more complex, potentially, right? It is acted upon by a variable force, and we'll say that force is f of x equals kx squared. Okay, So it's as it moves, it is acted upon by a variable force, f of x equals kx squared, that accelerates it. Accelerates the block. Okay, so it's already going 2 meters per second, and then some force starts to act on it at position x equals 0 meters. And then once that force starts acting on it, obviously it's going to accelerate. Okay, and so then what we're told is at x equals 5 meters, the block speed has increased to 6 meters per second. Okay, and two things we're interested in finding here. One, let's find the total work done. And we'll say between x equals 0 and 5 meters. Okay, so the first 5 meters of the displacement is 5 meters, right? So let's figure out what the total work done over that interval is. And then secondly, let's identify this constant in the variable force function. So let's identify k in f of x. We need to figure out what that constant is, right? So it's kind of like a spring constant, but it's not really, because this is k times x squared. So it's proportional to the square of the displacement. So it's a little different, right? Well, we're not told what any of the forces are. I mean, we have the generic force function, but we're told the initial and final velocities. So that being the case, we can use the work energy theorem, right? So let's start by calculating the initial kinetic energy. So that's just 1/2 mv1 squared, which we have all those quantities. So 1/2 times 3 kilograms times 2 meters per second, quantity squared, is 6 joules. Okay, and then the K2 is again 1/2 m, but this time the final velocity, K or V2. So 1/2 times 3 kilograms times 6 meters per second squared. So it's accelerated up to 6 meters per second significantly. It's tripled in speed, really. And so that is 54 joules, right? So that means that the total work is equal to K2 minus K1, which is 54 joules minus 6 joules. And that means it's, 48 joules, right? So we got 48 joules of work that's been done by this variable force. Okay. All right, so that tells us item 1. Now, using this information, we're going to work on item 2. We want to figure out what the constant is in this function. Okay, and so we're going to use the integral version of the work definition, right? So we're going to say work is equal to, in this case, 48 joules. Now there's an integral here, right? So it's the integral of f dx over the displacement. So the displacement is from 0 meters up to 5 meters, and the force function is kx squared, and then we need to integrate that with respect to the displacement, and we'll call that dx. Okay, so this is a super easy integral. This is just k over 3x cubed, and then from 0 up to 5. And so we can calculate this real quick as k over 3 times the quantity 5 cubed minus 0 cubed. And so what we see here is that 125k over 3 is equal to 48 joules. And so that means our k, and I'm not going to worry about the units right now, k is equal to 48 times 3 divided by 125. Right? And you do all of that, you get k is equal to approximately 1.15. Right? So that's the constant in this variable force function, this square kx squared. So it'd be the f of x is equal to 1.152 x squared, right? So f of x is equal to 1.15 x squared. Okay, that's the function. All right, very good. right? So kind of a different, slightly different angle on work and kinetic energy. Very good. Let's take a look at another one. This one will be a little more involved again. Nothing too crazy, but again, just trying to kind of pull together some of the different connections that you might find when you're working on some of these. So a 4 kilogram block is pushed up a rough incline. Is pushed up a rough, and I'm going to quantify that. The kinetic friction coefficient, mu sub k, is equal to 0.1. So a 4 kilogram block is pushed up a rough incline that makes a 30-degree angle with the horizontal. Okay. All right, and so again, we're going to have a variable force. So a variable force, and here's that force function, f of x equals 200 minus 5x newtons. A variable force is applied parallel to the incline. Okay, it's applied parallel to the incline. All right. The block starts at rest at the bottom of the incline. Starts at rest and is pushed 10 meters so the block starts at rest and is pushed 10 meters up the incline. Okay, identify the work done by gravity. The work done by gravity, the friction force, and the applied force. Okay, and then after we've done all that, let's find the speed of the block at x equals 10 meters. Okay. All right, so kind of a lot of words there. But what do we got going on? It's a pretty simple situation, actually. We've got this incline, right? Like, very popular thing to have when we're dealing with work problems. We've got a 4 kilogram mass that we're pushing up this incline. The displacement is going to be 10 meters. Okay. This one is a little different than the previous ones because we have a friction force in play as well. So we've got a variable applied force, meaning somebody pushing on the thing with some variation, and then we've got a friction force, right? And then of course we've got gravity also. So let's think about the free body diagram. So we've got the weight pulling the thing in this direction. We're pushing it up an incline, so maybe the incline is like this, right? Kind of like, and so we're pushing this variable force. We'll just call F, and then I'll sub it with applied. Okay, the applied force is in that direction. It's offset by a friction force that's in the opposite direction, and of course we have a normal force that's perpendicular to the incline. Okay, so this is pretty much what the free body diagram would look like. Okay, so this is the free body diagram. All right, so it turns out really that the easiest force to deal with here, so we want to calculate all the work, right, for each of the forces. So we've got 1, 2, 3 forces we need to calculate work for. And it turns out the easiest of them is the applied force, even though it's the variable force and requires, us to think about an integral. It turns out it's the easiest, right? So the work done by the applied force is equal to, it's an integral, right, over the displacement from 0 to 10 meters. And the function that we're given is 200 minus 5x. And then we're going to integrate with respect to x. So this is 200x minus 5 halves x squared. That's what that integral is. And then we evaluate it from 0 up to 10. So that would be 200 times 10 minus 5 halves 10 squared. And then minus, and then these evaluated at 0 is just 0. Okay, so you've got like 2,000 minus, 500 over, well, yeah, minus this thing. So that would be altogether about 1,750 joules. Okay, so the applied force, the push, whatever's pushing it up this hill, is doing about 1,750 joules worth of work. Okay, very good. So this is the applied force. Just put F, applied. Let's next look at the friction force. All right, so remember the friction force, you've got the weight, you've got a normal force that's kind of perpendicular to the surface, and then the friction force is acting in this direction, isn't it? Okay. So what is the normal force? Well, let's think about that. The normal force is equal to basically the weight, right? But it's not exactly the weight, it's just this component here of the gravity, right? So it would actually be mg cosine of theta, where theta is the 30 degrees, right? So we get, well, we'll just leave it at that for now to start with. So that's the normal force. And we know we need that, right, because the normal force is what kind of helps dictate the friction force. So the friction force then is equal to the normal force times the kinetic friction coefficient, which was a given. Right, so altogether this is mu sub k times mg cos theta. And so we have all of these quantities. We can plug this in. It's important to note that this is a negative force just based on the way we coordinatize this thing. It's heading in the negative direction. So we're going to make it negative. Okay, and so this would be negative 0.1 times the mass, which is 4 kilograms, times gravity, 9.8 meters per second squared, times the cosine of 30 degrees. And so the friction force is equal to negative 3.39 newtons. Not a very strong friction force. Okay, remember the applied force is 1,700 joules. So this isn't going to get us even close to that. So this is negative 3.39 newtons. So what's the work done by this force? The work done by friction? Well, it's equal to this friction force times the displacement, which in this case is negative 3.39 newtons over 10 meters. So 33.9 joules. Okay, so we've got a 1,750 joule work being applied in the positive direction. That's being offset now a little bit by the friction. Okay. And then we know additionally that not only is friction pushing this thing back down the slope, but also gravity. Gravity is also pulling the block back down the incline. So let's take a look at what's happening with gravity. So here's your block. There's mg, right? Dragging it down. The gravity component that's aligned with the displacement is kind of like this. I'm just going to denote it g sub x, right? And so you've got a right angle here, okay? And so the sine of 30 degrees would be equal to this g sub x over mg, right? So it'd be, this is mg here, and so you can kind of see where that's going to go. And so that means g sub x is equal to mg sine 30 degrees, which is what, well, m is, again, this is negative, let's be careful here. So negative 4 kilograms times 9.8 meters per second squared times sine of 30 degrees. Okay, and all of that is equal to negative 19.6 newtons. So that's the force of gravity that is aligned with the displacement. So this is the force of gravity that is aligned with the displacement. We need to know that part of it, right? We're not interested in the total weight, right? We just need the part of the weight that's pulling it back down, that's aligned with the displacement. In this case, it's opposing the displacement. Okay, and so once we have that force, we can calculate the work that's done by it. Okay, so the work done by gravity is just equal to negative 19.6 newtons for 10 meters. So negative 196 newtons. So the gravitational work, the work done by gravity is, this is joules, sorry about that. The gravitational work, the work done by gravity on the block is quite a bit larger than the friction, but they add together, right? So you got about 34 joules together with 196 joules. And so you've got, a little over 200 joules opposing the main force, right? And so then the total work is equal to the 1750 joules by the applied variable force, and subtract from that the 33.9 joules from friction, and then subtract again from that 196 joules due to gravity, and altogether you get about 1520 joules. And so that's approximately the total work, right? The total work is approximately 1520 joules. Okay, so that's kind of the first part of the question. A lot of stuff in that. If you look at it, we did a lot of little work calculations there. But once we have that, the second question is, what is the velocity at the end of the displacement at x equals 10 meters? So to find the velocity at x equals 10 meters, right, what do we have to do? Well, we're going to use the work energy theorem. The total work is equal to the change in the kinetic energy. Okay, and so we know that the initial kinetic energy is 0. It's at rest, right, initially. And then we start pushing it up this hill, and it's going to be accelerating up this hill because there's a net force. And so we know that 1520 joules is going to be equal to this final kinetic energy, which is 1/2 mv2 squared. And we know m, and what we want to know is v, right? So I've got 1520 joules equals 1/2 times, what is the mass here? The mass is 4 kilograms. Okay, and so v2 is the square root of 1520 joules times 2 divided by 4 kilograms. You do all of that math, and you get 27.57 meters per second. All right. So this thing starts at rest. You start pushing it with a pretty significant force. The force varies as the displacement changes, and the net force is definitely in the rightward direction, meaning uphill. And so this thing is going to pick up speed very significantly, in fact. And by the time it hits the top of the displacement, 10 meters, it is going almost 28 meters per second. All right. Very good. So a lot involved in that problem, a lot of different pieces. Okay. Let's do one more example. Okay, I think this one is just a little bit different. Requires a little. It's kind of got some deep cuts in it. The example says a motor lifts a 50 kilogram crate vertically. A motor lifts a 50 kilogram crate vertically with a constant force over a height of 15 meters. Okay, and it says the lift takes 3 seconds. Okay, we want to calculate the total work done. Calculate the total work done by the motor and find the average power over the lift. Okay, so what is going on here? So let's just draw it like this. Here's how I have it pictured when I was coming up with the problem. You got some kind of a motor, right, and it's attached to this wheel apparatus. You know, it's just kind of hanging from the ceiling or something, right? And then you've got like a rope that's dangling off of this thing, and then you've got, you know, like a crate or something that the rope is tied to. Right? And it's just pulling this crate up into the air. Okay, and specifically the displacement is 15 meters, obviously not drawn to any kind of scale whatsoever. Okay, so you just need to drag this thing off the ground about 15 meters. All right, and so the question is, what's the total work done by the motor? And then if we know that, since we know that it takes 3 seconds to lift this thing up this far, can we find the average power over the lift? Okay, so we're not given any kind of force here. What we can do is we can use some kinematics to identify the force the motor exerts, specifically just by using Newton's second law and thinking about what the acceleration is. So we have to start by finding the acceleration of the crate. So start by identifying the acceleration. Okay, and so how would we do that? Well, if you think back to our kinematics, we had this expression x, this equation x of f, the final position equals the initial position plus the initial velocity times time plus 1/2 at squared. Well, in our case, the initial position is 0, the initial velocity is 0, so the final position is equal to 1/2 acceleration times the time squared. Right, so we have those quantities. So we could say 15 meters is equal to 1/2 a times the time, which is 3 seconds squared. So we could figure out what the acceleration looks like over this 15 meters, right? Now remember, this is a constant force, right? So this kinematics equation only really works if the acceleration is constant, which it would be in this case. Okay, and so the acceleration then would be just 15 meters times 2 over 3 squared, 3 seconds squared. Right, and so that'd be 15 times 2, so 30 divided by 9 basically. And so you get 3.33 meters per second squared. Okay, and so this is the acceleration that the crate undergoes as it's being lifted 15 meters into the air. Okay, so once we know the acceleration, we can calculate the total force applied by the motor. Right, now if you think about it, the motor is going to have to overcome gravity, right? Obviously it's pulling upward, so it has to oppose gravity. In addition, it has to oppose gravity enough to generate the required acceleration, right? And so let's think about Newton's second law. Newton's second law would say that the net force is going to have to equal mg, that's gravity, right? The weight of the object, plus it's going to have to exceed this by enough to get this acceleration, so plus ma, right? So this would be m times g plus a, and if we plug in those quantities, that'd be 50 kilograms times 9.8 meters per second squared plus this 3.33 meters per second squared. And whatever this quantity is, that's going to be the required force to make the physics of the scenario actually work. Okay, and so the force is going to be equal to 50 kilograms times this sum, which is 13.1 meters per second squared. multiply all that together, and you get about 655 newtons. Okay, so about 655 newtons. All right, very good. So that is the force that the motor is exerting. So now the question is, what is the work that the motor does? Okay, so if that's the force that the motor exerts, so F is equal to 655 newtons. What's the work? Well, the work is just equal to the force times the displacement, which is equal to 655 newtons times that 15 meters, right? We got to lift at 15 meters. You apply this force over that displacement. And when you do that, when you multiply that together, you see you get 9825 joules, so almost 10,000 joules of work. Okay, so in order for this crate to lift this thing off the ground and to accomplish this displacement in 3 seconds, you gotta have about that much work be done. Okay, well, you gotta have that force, and then specifically that accomplishes that same amount of work. And so then the second part of the thing is just, well, what's the average power? That's very simple, isn't it? The average power is just the change in the work divided by the change in the time, right? And so in this case, 9825 joules, that's accomplished in 3 seconds. And so the average power is 3,275 watts. Okay. All right. Very good. Okay. So that kind of concludes it. Again, we did a lot of examples in the sections before this, but I think some of these are good to do. It's always good to do more examples, see more examples, read more examples. It always helps. And so I think in this case, we'll call it quits with that. When we come back in the next lecture, we'll be discussing. We'll be kind of shifting our focus to potential energy. We'll get kind of moving away from kinetic energy and going towards potential energy, and then the principle of conservation of energy as well. So very interesting stuff to come, but we'll leave it at this for now. Until next time, take care.